So now I'm going to go ahead and calculate the estimated Cohen's d. And in this formula, we've got m1 minus m2 minus mu1 minus mu2. Just like before, that goes to 0 for the same reason, right? Our null hypothesis, which is always what we're testing, is that they're equal, that mu1 equals mu2. And if you have 10 minus 10, a million minus a million, it's always 0. So that goes to 0. On the bottom, we have the pooled standard deviation. We haven't calculated that yet because we had equal variance or equal sample sizes. So we could bypass it when we were calculating the estimated standard error. In order to calculate this pooled variance, we are going to use degrees of freedom 1 times the variance of group 1 plus degrees of freedom 2 variance of group 2 divided by degrees of freedom 1 plus degrees of freedom 2. The degrees of freedom of each group is n minus 1, which in this case is 12 minus 1, so 11. And we weren't given the variance. We were given standard deviation, which is something different. But if you recall, down here when we were calculating this estimated standard error, we did take the standard deviation and square it already. So I'm going to pull this number, 1.08 and 0.85, over to my calculation of the pooled variance. So 1.04 plus, and the degrees of freedom of the second group is the same because they had the same sample size, and put 0.85 here, divided by 11 plus 11. So 11 multiplied by 1.04 is 11.44. And 11 multiplied by 0.85 is 9.35. And we'll divide that by 22. So I take 9.35 plus 11.44, and that gives me 20.79 divided by 22, which is 0.945. That's the pooled variance. I need the pooled standard deviation. So the pooled standard deviation is the square root of the pooled variance. So I'll take the square root of that number that I just found, and that's 0.97. Let's just keep 2 decimals for now, okay? So now I can take this number and plug it up here into my formula for Cohen's d. Group 1 had a mean of 5.2. Group 2 had a mean of 4.3, and I'll divide by that pooled variance. So on the top, that was 0.9 divided by 0.97. I'm expecting something slightly less than 1 because the denominator is larger than the numerator, but not by much. I get 0.93, which is a large effect size. Anything above 0.8 is generally considered a large effect size.